Hello, welcome to today's webinar, Ready, Set, Scale, Deep Learning for Defense Applications. My name is Jody Lee, and I'll be moderating this webinar. I'm excited to be joined by Will Rohr, Program Manager at Harris Geospatial, and Pedro Rodriguez, Solutions Engineer at Harris Geospatial. They have a lot to cover today, so really quick, I'm going to cover a couple housekeeping items before we get started. I've muted the phone lines for all attendees, so at any time you have questions, just enter them into the questions chat box on your GoToWebinar dashboard. Will and Pedro will answer as many as they can at the end of the presentation. We're also recording this webinar, and we'll email you a recording along with the slides and a couple other things in the next 24 hours, so look for that in your inbox. And I encourage you to share it with any of your colleagues. So without further ado, I'm going to turn things over to our first speaker, Will.
All right, good afternoon. Again, my name is Will Rohr. I'm an account manager with Harris Corporation. I've been with Harris over 16 years now. I've been focused on geospatial applications and services for the Defense Department and intel agencies. And today we'll talk to you about how we're applying some of the latest technology and deep learning to defense problems. So real quick agenda, I'll give just a quick background on who Harris Corporation is, where we come from and which group we're talking to you from. A call to action on the DoD's adoption of artificial intelligence, machine learning, deep learning type of technology. Some of the research we've done in deep learning. Pedro will walk us through several of those applications, and we'll close out on how Harris has been working to scale up that type of adoption for the DoD.
Okay, great. I will give us a starting introduction here, letting you know who Harris Corporation is and which group we're presenting to you from. So Harris Corporation is a top 10 defense contractor divided into 3 large segments. Our communication systems division is the Harris radios you see all over the world, as well as night vision technology. Electronic systems is the group that works a lot with electronic countermeasures, electronic warfare systems that are on many of the airframes out there. And then space and intelligence systems. This is a group that focuses on space-based sensor manufacturing, as well as airborne, the downlink ground processing, all the way out to the dissemination and exploitation, kind of a glass-to-glass geospatial-focused group there. And Pedro and I are presenting from that group, specifically inside of that segment, the Harris Geospatial Systems inside of Space and Intelligence Systems. So with that being said, I'll get us started on the urgency behind the DoD's adoption of AI. Just to kind of set the stage, we know the digital universe is exploding both in the commercial sector as well as in government sector. With the explosion of video devices on cell phones, the various sensors that commercial and government entities are flying in space and the air, digital data is just exploding. Many different ways of representing that, but it's exponential growth. How that affects the DoD, there's been a variety of public statements from figureheads within the DoD over the years. They've seen this coming for a while. Going all the way back to 2010, a very famous comment from Lieutenant General Deptula from the Air Force that he mentioned, we're going to find ourselves in the not too distant future swimming in sensors and drowning in data. And this is when they were launching many of the new UASs and the exotic sensors they were carrying. More recently, Robert Cardillo, director of NGA, speaking to the advent of the small sat revolution, said we were going to witness a darkening of the skies. So many commercial small sats were going to go up, and a flood of data to follow with that. More recently, in 2017, Robert Cardillo also stated that we've reached the point that even now, every day in just one combat theater with a single sensor, we collect the data equivalent of 3 NFL seasons every game in high definition. And if we were to try and exploit all of that data that's coming in, we'd need 8 million imagery analysts. And most recently, in the NGA 2022 GEOINT ConOps, just flat out stating, Robert Cardillo said that we have grown beyond the limits of human interpretation and explanation of the data that we're collecting, and we have to adopt some sort of automated processing to handle this enormous amount of digital data. So with all that statements made by the DoD, and we see the wave that is upon us, in the commercial sector, there's been a deep learning revolution going on, a resurgence of artificial intelligence and machine learning capabilities. It's best represented by the ImageNet challenge that's been running since 2010 timeframe. This is a worldwide challenge for computer vision pattern recognition type of applications that provides a very well curated set of training images divided into 1,000 different object categories. These are all forward-facing images, kind of like what you would see from a cell phone, but the point of the competition is to apply the best and brightest technology we have to automatically characterize and classify that data. Each year, the results are compiled and there's a winner selected. The chart in the upper left shows the error rate on that ImageNet challenge. Things to note, between 2011 and 2012 was the first entry of a convolutional neural net powered by a GPU. And that showed a 10% spike year over year, and that's really the watershed moment that we have a new powerful technology to take a hold of here. Neural nets had been around for years, but powering them with GPUs made them feasible to use on this type of technology. And it continued to improve as the models got deeper and more refined. Between 2014 and 15, it exceeded human level error rate, accuracy rate, and continued on down into last year's winner actually went below the 3% error rate. So very powerful technology for computer vision type of applications, and that has caught the attention of all of the big commercial companies out there. Acquisitions have gone off the charts for artificial intelligence, machine learning, computer vision type of applications, and represented by all of these mergers and acquisitions. All of that's happening in the Silicon Valley commercial sector, and that's what the DoD is seeing, knowing they have an enormous data problem, as indicated by the previous statements by our Cardello and company. So all of that, those two things together resulted in the Defense Innovation Board earlier this year providing this statement when they looked at the problem, ultimately resulting in the significance of artificial intelligence and machine learning is akin to the first and second offsets that took advantage of nuclear weapons, precision munitions, and stealth technology. That's the level of importance the DoD is seeing in bringing in the benefits of AI into the various applications, starting with C4ISR, but then moving into all the different areas of the DoD's logistics, training, force protection, and so on. And so that is what's behind the urgency. And so what we'll do is show you some of the examples of how deep learning can be applied to certain geospatial type of problems, the obvious benefit there, and then we'll move into how we're making that technology scale up for defense level applications. So with that, we get to the first poll question. What is your organization's current level of artificial intelligence machine learning adoption? Answers being not yet, doing research and evaluating solutions, are in the starting phase, starting to do some prototyping, or fully operational. And so I think you'll see pop up on your screen the questions here if you'll go ahead and get those answers in place, and we'll take a look at the results here. Okay, I think we see the results come back here. Much as we would expect, this is a very new technology, so we're seeing the results come back from the poll here is majority of the respondents, over 50% here, are still in the doing research, evaluating solutions phase. Some, about 25, maybe 30%, are in the starting phase, starting to prototype. And some haven't, third category there is haven't even started yet. And then a very small sliver are fully operational with machine learning, deep learning applications. So understanding where the community is at, I think this is representative of the community as a whole. We'll take a look at some of the applications we've done to date and then switch over into how we scale those. So I'll hand it over to Pedro Rodriguez to take us through some of the applications.
Great. Thank you, Will, for setting us up with the importance of machine learning in the defense and intelligence community, especially for national defense. Like Will mentioned, I'm going to be talking about some of the pilot projects and commercial solutions we have found for customers at Harris. So actually, Harris, realizing the importance of machine learning, they have made a multi-million-dollar investment into applying state-of-the-art deep learning technologies, but translated into remote sensing and GEOINT customer problems. That investment has been divided in, first of all, doing research, following the latest developments in industry and academia, mostly in optimizing the learning process of the neural networks. And then we go on into applying that research into pilot projects based on the customer feedback that we get, and then push the boundaries on the possibilities that we can achieve with these algorithms and technology. And then also we focus on software development, ease of use of our tools to make them into commercially viable products. We're also focusing on 4 main areas, starting with training. This means reducing the cost of training, creating highly accurate models with the least training data. One of the things that Will is going to cover later is the importance of labeled data and how we're working on reducing that cost of training so we can produce these accurate models with limited training data. The next focus area is extensibility, being able to work with different deep learning engines like TensorFlow, Caffe, Torch, and Keras, because each one of them offer their pros and cons, so we want to be able to plug and play each one of those into our framework. Also, it's very important to include multi-int solution into our capability. We understand that most of our customers don't have label data of the same data type, so we're going to be able to provide multi-int deep learning models to take into consideration multispectrum imagery, panchromatic, SAR, Lidar, or any other type of data that our customers have available. And then most importantly, automation, being able to provide activity-based intelligence and provide that end-to-end solution for customers, from gathering label data up to providing activity-based intelligence based on the detections. So at Harris, we actually started about 6 years ago, doing mainly overhead analysis, and we have gotten really good at it. Up upper 90% accuracy. We feel very confident. We have tested in multiple targets, and you can see a list there on the right. And also, we're showing 2 examples here. The left example, we trained an airplane finder with high-resolution conventional imagery from different sources, like Equinox, QuickBird, or View2, and then running that through a panchromatic image of the Tokyo International Airport. On the right side, we did a crosswalk finder in images from Sao Paulo, Brazil, 30 centimeter resolution, and we found all the 43 crosswalks in the scene with 0 false positives. At this point, it's ubiquitous to find objects into the overhead imagery. So we wanted to provide geospatial context to detect, not just finding objects, but what does it really mean? So we did this pilot project internally where we took a data set actually that is open and available. It's 8 centimeter data of Washington, D.C. If you want to see it, it's on opendata.dc.gov. The goal was to find crosswalks in the city, specifically zebra type crosswalks and versus non-zebra type crosswalks, and correlate that information to the pedestrian accidents happening in Washington, D.C. For that, we use we merge our technology of machine learning with insights for ArcGIS. So we were able to overlay that vector file with the crosswalks on top of a web map service, and we were able to see those black dots there represent the accidents happening in the city. Some of them happening in crosswalks with zebra type crosswalks, and some of them, and a lot of them actually happening in the non-zebra stripe crosswalks. So after analyzing our results, we're easily able to find those notoriously troublesome crosswalks that were causing a lot of accidents without zebra-striped crosswalks. So this is an example of how we can apply deep learning technology to aerial imagery, and within hours we can find pretty much all the crosswalks in the city and correlate it to GIS information that is freely available in the web. The next phase of 2D overhead is actually performing target subclassification into objects that are very similar. So this is currently in R&D, and the goal is to use the same data set that we use for the crosswalks, but to identify red cars versus red taxis. This is happens to be a very challenging problem, especially because the difference between these two cars is mainly 7 pixels across the car. That is the fin that the red taxi has. So we're currently modifying our algorithms and see how we can solve this type of problems, which, based on the feedback we have gotten from our customers, is very important to solve. On the next example, I already covered 2D overhead, but now we're going to cover a little more of drone imagery. In this example, we actually partnered with a company called Edge Data. We built a tool called Blade Edge. And it's for performing automatic blade inspection of the wind turbine. It actually can ingest the 15 to 20,000 images that it collects, run that through a machine learning algorithm to find the defects on the wind turbines very easily and automatically. It's actually an example of the UI. It actually generates a report for the users. Here at the top, you can see a co-registered mosaic of the entire wind turbine blade. In this case, it's the high pressure side of the wind turbine A. And it also provides not just where the damage is, but also what kind of damage and the extent of the damage. So in this case, it's actually EPRI code number 2, which means it's a blue major cosmetic damage. And if the user wants to inspect further the damage, they actually can get a high resolution image of the wind turbine. On the next use case, we actually partnered with Planet to use small sat data to take advantage of the high temporal resolution data of their data. As of today, Planet is able to image the entire Earth every day. So finding illicit airfields in South America was a perfect pilot project for proving out this technology. So in this case, we actually, we're focusing on not just finding the airfields, but how they were changing over time. As you can see here on the image, in May of last year, there was no airfield, and then, next, there was the airfield was operational. 1 month later, it was cratered. Local authorities there, when they find an airfield, they bomb the airfield, so it becomes non-operational. So being able to find that type of activity is very important for combating this type of activity. We tested with multiple type of neural network architectures, single frame, temporal, and LSTM, which are both recurring neural networks, and they perform about 4 to 5% better than just single frame architecture. On this next use case, we actually did this work for a French railroad company to perform asset inventory using 3D Lidar. In this case, a sensor was mounted in a train, collecting point cloud along the tracks, and then being able to extract the information they needed for the asset inventory, like pole crossings, any other type of poles, and it was very highly accurate. We were using a fully 3D convolutional neural network for this case. In this next case, it's actually a commercial product available today as a Harris product. It's called Helios, and it provides hyperlocal weather information using traffic cameras. And what it does is every 5 minutes it analyzes a single frame to detect road conditions, either wet, either dry, and then send that information to our customers as an API. This is an example of the UI for Helios. As you can see, we have a network of cameras in the continental US. We have about 50,000 cameras online at the moment. It actually has expanded internationally recently. We're planning to expand the network of cameras for Helios, but it is constantly monitoring the weather using these very low resolution cameras. This actually, for the next phase for Helios, is going to be used for both for navigation and for autonomous vehicles, implementing the same technology in detecting road conditions applied to the forward-facing cameras in the cars. It's able to detect road conditions and then send alerts to our users, either to the dash navigation or to their phones. We actually have partnered with several car companies, including Subaru, other manufacturing companies like Clarion and Hitachi. We're working closely to bring this technology to cars. On the F&B side, the next phase is actually providing F&B analytics to translate the analytics that has been done on the traditional security type cameras, but applied to overhead video, like those we see from like predator feeds. This problem is obviously more challenging than traditional security cameras. You have fewer pixels on target. The gimbal is less stable. It's constantly changing orientation, different modalities, different zoom levels. But this is going to be crucial, and the DoD is taking steps, towards achieving this goal. Like Will mentioned, right now, every single theater is collecting 3 NFL seasons per day. So being able to apply this technology to F&B analytics is going to be crucial, and Project Maven is going to be one of those steps in that direction. So lessons learned, from my talk, it's pretty much 3 of them. We have proven that we can perform automatic target recognition with multiple data types. It could be MSI, panchromatic, SAR, or Lidar. We're growing that number, taking in also derived data types or any other data type that our customers have. We also have proven that we can perform very highly in the upper 90% with the condition that we have the appropriate neural network architecture and label data. Will's going to cover how we're solving some of those challenges that our customers might have, when they want to scale this technology. Now next, everything is pretty much fueled and enabled by the very powerful GPUs. Like Will mentioned, none of this, would have been possible, with very powerful GPUs because they're so dependent on powerful computing, and the folks from NVIDIA have been great in providing that computing power. Instead of taking days, now it only takes minutes to perform these calculations. With that, I'm going to leave you with Will, so he can go into how we're going to scale this technology for the defense industry.
Okay, great. Appreciate it, Pedro. Right, so as Pedro showed, there's a ton of applications for deep learning across the geospatial type of problem sets, and very easy to get some high reliably accurate answers there. And so now we should start focusing on how we scale that out. And I make this slide just as kind of an introduction to the various different components we need to think about when scaling out. It's easy to see all the buzz in the various different sectors here on adoption of AI, that if I've got a problem, some sort of big data problem. I throw some machine learning at it. I'm going to get some answers at it. Let's just do it. Well, if we go a level deeper, what all does that involve? Many times we're still requiring a PhD data scientist, either for the neural net architecture or for the big data problem in general. We're going to need a ton of training data. In the past, doing this through traditional techniques, we would need an image scientist or a specialist on the target we're trying to find. Now we don't need that, but we're going to need a ton of training data. We're going to need that data very labeled accurately, and we're going to need it highly curated so that it's formatted properly for the architecture we're trying to adapt to our problem set. We're going to need hardware. As Pedro mentioned, a lot of hardware. This is very compute intensive. GPUs solve that problem, but you still need a lot of compute power to get it done. Specifically in the DoD space, we're going to need to understand the data ingest, the various components of the metadata that's associated with the data we're trying to use. A lot of the DoD sensors have very specific metadata attributes that go along with it, the geolocation information with it. We want to maintain that throughout our processing chain. We're going to need to have a very core understanding of the problem that the customer has and how we're going to present the solution to them. There's a variety of different ways that we can provide the answers, from heat maps to single pixels to bounding boxes to so on. We're going to want to retrain these models to keep them accurate over the initial area that we are wanting to apply it to, and then expanding it into other areas beyond the original training data set. And then a variety of other things, just a whole surrounding set of issues that we have to keep in mind. What type of platforms are we distributing the answers to? Is this going to be run or visualized in mobile applications? What type of performance are we going to monitor of the algorithms? How are we going to notify the people that are using it, continue to refine it, the ortho-rectification of the data that's going to be used on that algorithm, maintaining all the geographic data. And then after we build these things, what are the export controls of the various different type of algorithms we've put together? All of these different things are just kind of representative of there's a lot that goes into scaling up the adoption of AI. So I use that to set the stage for the scaling discussion, and that kind of introduces us to the second poll question we have here. So I'd like to ask the audience, where do you see the biggest challenge for the adoption of machine learning and deep learning technology? Is that in the availability of the label data? Is it the selection of the neural net architectures for the problem you're trying to solve? The various training and retraining techniques? Am I deploying transfer learning? Am I training after I put it into operation? The end-to-end infrastructure to tie this all together? Or the interpretation of the results, the visualization? How do I show it to an analyst that doesn't overload them with information? Because that's ultimately what we're trying to burn down anyway. So we'll leave that open. I think you should see the questions on your screen, and we'll look for the results to come back here. It looks like we've got the results, and I'll flash those up here. Okay, it looks like the biggest challenge that the group sees, and this is kind of representative of what we're seeing and hearing from the community, is the label data challenge. Of course, we can get very high accuracies with these techniques, but we've got to have a lot of examples of what we're trying to teach the neural net to find. Followed by in infrastructure, and then closely after that, the interpretation of results. So this is representative of what we're hearing, and I think you'll see how we divide this up and strategize our approach for scaling this technology. So we'll step into that. If we lay out those different challenges, we kind of organize them into different layers or tiers that we're applying our investment to. At the lowest layer, you have the source information. This is the data that's going to be the label data we train the neural net on. How do we get that label data? Is it manual harvesting? Are there ways to synthesize it? Are there ways to do more with less? Above that, we certainly don't want to leave any information on the table. Many of the collects today, most of the collects today have co-registered simultaneous collect of other modalities. Can we put that to use? Certainly we have existing data in various vector databases that we can use to help either gather data or better inform the model. The whole art of the learning teaching process to the neural net, selecting the architecture that the neural net's going to use, and how we apply the training data to it. And then once we've trained a model, the infrastructure to support the use of that and the retraining and the passing of information from machine-to-machine systems. Once we generate observations or detections or recognitions of some sort, how do we pass that into downstream databases to make higher order decisions? And then the accessibility. How do we display that to an end user? What's the visualization we're going to use? What sort of blobology do we put into play to draw either polygons around it into shape files or into CAMZ files or the various different components there? And ultimately, applying automation to each of these, vertically across each of these, to make an end-to-end process. That's the way we are trying to apply our investment here to scale up. And certainly, if we solve this in one specific ISR problem set area, maybe for a specific modality or for specific sensor, we want to rinse and repeat and do that over and over again. If we solve it in overhead PAN, of course, do the same in MSI. Let's do it in Lidar. Let's do it in FMV. Ultimately, where we're trying to get is tying all of these things together into a cognitive ecosystem with the end goal of getting to a higher order sense making, achieving that automated activity-based intelligence where we're no longer just looking for objects or features, but tying that information together over time and recognizing patterns and understanding patterns of life. But before we get there, let's go back to just zeroing in on the one set of problems to start cranking out these deep learning type of applications. In the first category, the source information. As our poll indicated, and we've heard widely in the community, the label data challenge is enormous. We come at it from 3 different angles. Obviously, just go get it. There are ways to make things more efficient in manual harvesting. There's techniques for crowdsourcing that may not be possible in DoD, Intel type environments. And what can we do with data sets that are already out there? We're not going to have labeled data sets sitting around for every target we're looking for, but can we use those to give us a jump start? Doing more with less, kind of using that jump start technology. Can we transfer learn? Can we synthesize the data? Maybe I never had any label data, but I can simulate or synthesize that to train a neural net. Got a slide on that later. Various techniques in unsupervised and active learning. Tons of different applications there, but all in the vein of trying to get off the ground running faster with less label data. So let's step through a couple of those. Just starting at the most basic, Envy, our flagship ELT program that Harris offers, available just about every analyst workstation across the services and agencies. We've built in some tool sets to allow more efficient labeling of data and providing that as a file that can be server-side chipped in volume. And what I've got on the screen is an example of labeling a multi-class vehicle set of label data. And then we can spit that out into a file that gets chipped on the server side. Just very basics, but covering all angles of let's enable the manual harvesting. Where do we go beyond that? We've done some experimentation and had some good success in using the deep embeddings of neural nets. And so the concept here is a neural net that has been trained on something completely different, a task that may be meaningless to the target you're trying to build a classifier for, ends up learning a lot about the world in general. In this specific example, we had the VGG16 model. This was a very popular model. It was one of the ImageNet winners several years back that was trained up on Places 2 location imagery, forward-facing images of various landscape type of scenery. If we take a very deep layer inside of that, snip off the end of the neural net where it was going to make the final classification and just use what it learned up to that point of the neural net, we can use that to group, to cluster label data. It's not going to tell me this is a road or this is a baseball field or this is a parking lot, but it'll say all of these are the same thing. And then an analyst can, in mass quantity, label those. Instead of labeling individually one by one, this is a road, this is a road, this is a road, draw a box around this entire cluster, all of these are roads, upping the efficiency for performing these label operations. Beyond that, I mentioned synthetic data. So one of the specialties Harris Space and Intelligence Systems has is in the realm of simulating imagery from whether it's space-based or airborne sensors. And so we have a many decades old history of applying this type of technology for customers before they put their multi-million-dollar asset into space. They want to sign off on the quality of the image that's being generated by that. And so we can use the radiometric model of the sensor along with tools like DeerSig from RIT that will make a physics-based representation of what the image would look like if you did take a picture with that sensor. And what we're able to do here is, even though I never had any actual imagery from that sensor, I can synthesize it radiometrically accurate and provide that over to a neural net to train on that. In this example, we had some fighter jets placed against a variety of different backgrounds, synthesize those images, and then train the neural net. And then on the far right-hand side, we have the detections from the neural net where it classified an image that it had never seen Iconos images of those fighter jets, only synthetic images, and then was able to find it. And this provides a way of augmenting and magnifying and generating a lot more label data that you never actually had any examples of to help you get through this label data challenge. Beyond that, going up to the next level, certainly we don't want to leave any existing information that's already on the table out of the picture when we're building these classifiers. There's a wealth of information that we have through GEOINT foundation data, vector databases that are out there, through things like NGA's Map of the World. These existing vector sets of information can be applied to neural net approaches across at least 3 different applications there. On the front side, we can use geospatially tagged items on the Earth to help us harvest label data. If I already know this is where certain facilities are that can cue me in to go chip that and then make that part of my training set, I can additionally use it for search space reduction. If I've trained up a very exquisite high-powered neural net classifier, I don't necessarily need to run that over every square pixel of that I'm collecting over area if there are areas that I know my target just would not be present in. So I can filter that out using this vector information. And then on the back side, the detections I am making with the classifier, let's use that to compare it against existing open sets and validate and add back to those databases. So a holistic approach and making sure we use the information that's available out there to inform and refine the neural net applications here. Outside of vector type of data and things that have already been identified, speaking to multiple types of modalities that can better inform the neural nets, one of the benefits of neural nets is they can take multiple input streams. They're data agnostic. As long as the information can be represented as an array, the neural net can learn from it. And so you run into situations where maybe I have overlapping corresponding panchromatic and MSI imagery that may be at different resolution layers, but I can use those as multiple streams to a neural net to better inform it. And then even crossing into different modalities, maybe I have MSI and Lidar and SAR, treat those all as streams going into it. And then beyond just mixing modalities, this is using a multiple stream technique is a way to augment the data that you do have. I can take the relatively few label data samples that I have and perform several image transforms on it and treat those as separate streams to increase the accuracy of my model. Got an example of that on the next slide. And of course, there's new data types coming out all the time with the various exotic sensors that are going up. So being ready to handle multiple data types at once is an area that we're focusing on. In this example, we applied one of our multi-stream neural net architectures for classifying roads in Mombasa. We used 4 different data types there. Each one, when used individually, did not give us very good performance on the road extraction problem. but when we combine those, we're able to get good results on pulling the roads up. To give you a little bit more quantifiable, at least visually represented the benefits that we're getting from that, I have an example of, on the right-hand side is one of our early airplane classifiers that we built. And this was with a set of hand-generated label data, and we only trained on that single set of panchromatic images. In that early model, we had a series of persistent false positives that kept popping up in our results. When we took that same set of label data and made two different transforms out of it, we had a radon transform and a log power spectrum, and used those as two additional streams to the neural net instead of just the original imagery, we achieved a synergistic decision there where we were able to burn down those false positives and raise our accuracy, as you can see on the left, getting rid of those false positives. Okay, so next we'll, once we've got our source information understood and how we're going to go after that, the various all source ints we're going to bring into the problem, the whole topic of the network architecture and how I'm going to train that, how I'm going to go through the training process comes up. We certainly don't want to start with start from scratch in building these architectures. We'd like to use something that's off the shelf if possible. The ImageNet Challenge has produced a ton of widely available neural net architectures that are well documented, well studied. Over the course of the years, they keep getting deeper and deeper. Again, this was for a problem that had a lot of pixels on target, kind of forward-facing images that you would see from a phone, and a lot of information. So the more memory your neural net had, 2015, it was all the way up to 152 layers deep. You kept getting more and more accurate as the years went on with the ImageNet Challenge. So much so that the contestants likely would say I was winning ImageNet until a deeper model came along, because that was the path. We keep going deeper, and that's how our accuracy goes up. But in the DoD space, much of what we're trying to do is not this large image or large target in a relatively small image with a lot of pixels on target. It's more of gigantic imagery with very small targets, very few pixels, and very few labels of the type of targets we're looking for. And so you run into the case of if I have very few pixels on target and not very many examples of that, the memory capacity of these deep neural networks may be so much so that it works against me. And I get into these overfitting situations. I get to where the neural net actually memorizes all the data I have and don't generalize against the targets I'm trying to find, which is one of the benefits we're trying to get out of the neural net. So what can we do to use these, even though they were designed for kind of a different reason, kind of the forward-facing approach? How can we apply those to DoD problems? One of the things Harris has looked at in applying these commercial-based applications for DoD type of applications is in the area of pre-training these networks. Can I pre-train the network to learn as much about the world in general so that when I do have a new target with a few examples, I can quickly pivot and retrain to that? In this example, we took the VGG16 model from the ImageNet. It was trained up fully on the ImageNet training data, 1.2 million samples with 1,000 classes, and we look at one of the deep layers inside of there, the COV0 layer, and you see the type of features it's pulling out in the first layer of pixels at the bottom of the screen here. And it's picking up basic edges, points, shapes, angles. That's the type of things it's learning, and we know that that's a high-performance classifier, high-performance network. If we take that same network and apply a convolutional autoencoder, and so this is where we're taking unlabeled data to try and pre-train the network and make it know something about that type of imagery, but we pre-train it with satellite imagery instead of the forward-facing natural images, you don't get the same type of feature recognition there. In the middle set of pixels, you can see there's a lot of noise. And so without making some modifications to make the jump into overhead satellite, less pixels on target, you don't get the same impact. So we made a couple tweaks to the convolutional autoencoder, and you can see our performance down there on the bottom just as an example. We are starting to get to those points and angles and edges and colors that it is picking up instead of just noise. So with a couple of tweaks, you can convert these things, these commercial-based applications, to be more relevant in overhead applications. Beyond that, if we talk about the specific network architecture, there's a variety of different ways that you can construct the architecture to be optimized for the problem you're going after. And typically, that's where you would have to bring in your PhD, your data science, your deep learning expert to understand the label data you have, the type of sensor you're using, and best construct an architecture that's going to pick up the signature you're looking for. And that's been one of the more time-consuming tasks when you set off to build a new classifier. What we've constructed is a tool we call Blender that is a form of auto machine learning that takes the label data that you have for a problem and optimizes the different layers of the network, the architecture of the network, to give you a best case scenario in picking up the signature you're trying to go after. And what this enables you to do is have novices sit down with the problem, not have to understand the various layers and interconnectivity of a neural net, but automatically pump out an optimized architecture and put it straight to work on building a high accuracy classifier. To represent how our Blender tool has impacted certain problems, again, I bring up one of our early airplane classifiers. On the left-hand side, we've got the results from a best human model. So this was a network architecture that we had PhDs sit down and hand construct for this type of data, for that type of problem. This is the architecture we should use. And we refined it over a long time and got pretty high accuracies. And then we took the exact same label data set, provided that to our AutoML tool, Blender, and allowed it to optimize the architecture, and actually saw a several percent improvement in the accuracy of the model. And so this was with no prior knowledge of deep learning architectures. I only had the label data that I want to solve the problem for. I automatically got a network architecture that's optimized over top of the best handcrafted model we could bring to bear. Another way to burn down a bottleneck for adopting deep learning.
Moving out of that, so once we've got our data, we know which multiple sources we're going to use, we've got a way of picking out our neural net architectures. How do we expose this to the various systems that are out there? How do we plug this into the infrastructure? So Harris has got a variety of tools that are in DoD spaces used for a variety of different reasons. One of them is Jaguar. This is a content management system we have deployed through several places in the Air Force as well as the Army, managing their overhead EO still shots as well as their FMV. And it provides large collection, archive and live, of a wide range of geospatial intelligence. And its purpose is to ingest it, catalog it, and disseminate it efficiently. All of the mechanisms have been tuned to efficiently disseminate that video. But now we have those large repositories. We know this wave of deep learning algorithms are coming that is going to be applied to data sets like this. We've been exposing those through APIs to be able to hook these deep learning algorithms in that and take advantage of all the metadata that's associated with them. And the shot on the bottom right there is an example of how Jaguar interprets FMV metadata, so we know where the sensor is, where it was looking at on the ground, what zoom level it was at, so I can more effectively apply which deep learning algorithm is applicable. So we've been exposing those assets, making them ready for the deep learning algorithms that are coming from ourselves as well as the rest of the community. Beyond that, beyond just opening up the repositories for exploitation with deep learning algorithms, tying these things together in workflow engines. One of the tools Harris has out there is the Hydra Framework in several of the government customer locations. This is a tool that was originally developed for rapid algorithm insertion, but in the traditional handcrafted SVM type of approaches. But you have an end-to-end workflow where you can register a new algorithm, define the processing workflow, define a watch box that it's going to be applied to, automatically kick off those analytics, ingest the content, run it, register the outputs, and then spit those out to the end user. We've this is perfectly suited for accepting these new deep learning algorithms that are going to be rapidly inserted here. One of the benefits of this type of workflow engine that we've been preparing for deep learning algorithms is the algorithm marketplace function. So we're taking advantage of the characteristics of the different algorithms, which data sets they work on best, and tying that back into the end user interface. So the user doesn't have to know this algorithm really only gets that accuracy over this type of image. Let's use that knowledge of the algorithm and the data sets to present it in a fashion where the most applicable algorithm for the problem gets presented. And that's kind of driven by that ontology to drive smart algorithm execution. An example of that, kind of bridging the gap between infrastructure and accessibility, is on the front end. So Hydra's more back end managing that workflow. One of our analyst views of geospatial analyst workflow is Dagger. And we've built in some machine learning plugins inside of that tool to help close the loop in the use the analyst is given of these classifiers and apply that for retraining methodology. All right, one of the great things about deep learning is as we put these into operation, we don't necessarily need to wait for 100% accurate classifiers before we put them out there. We can start using them much through this was brought up over and over by General Shanahan in the Project Maven charter, that the concept of prototype warfare. Let's put them into use, even if they're at 80%, and through the natural use of the tool, we can feed that information back into the algorithm to refine its accuracy. So we've built a UI to help display the results that let's say an 80% classifier has out there, and when it's making some false positives or some false negative guesses, allow the analyst to quickly go through those and evaluate them as yes, that's good, or no, that's bad, and then feed that information back into the neural net for retraining and increasing the accuracy. So the existing classifier tips the analyst to where it thinks things have been detected, and the analyst can evaluate those and feed that back to the machine, increasing the accuracy. And then kind of at the top level, the accessibility, how we're going to display these. Different use cases call for different things. Maybe I want a center point on the target, kind of like what we have here. Maybe I want an outline of the object we've identified. Maybe I want it fully segmented. But I need to be able to plug it into other systems and understand the metadata that went with that, and when was this algorithm run on which image, so that I understand how to display them. We're working on all of those different visualization mechanisms, whether it's an interactable single dot on target, or pushing out shape files, or in this example on the bottom right, KML type of files to display over the globe. Working on all of those different visualization techniques to show the different detections. Where all of that is taking us is tying all of this together for kind of end-to-end automation. And I bring up this last use case or project we're doing with the UK Ministry of Defense, was tying together multiple detection algorithms and aggregating that information and watching it over time, ultimately trying to get to activity-based intelligence. In this case, we were monitoring an airport in London, and we had incoming data feed, and we had the airplane finder watching it and monitoring the traffic. Taking that data and putting it into a catalog and monitoring it over time, and then presenting it in a way that doesn't overwhelm the analyst, but allows them to make quick decisions based off of changes over time. You can see in the upper right, we kind of make a heat map of how many airplanes are moving in and out of the area of interest, and the amount of traffic over time in the bottom right. You can quickly see there was a spike over that one weekend, and the further analysis showed there was an air show at that little airport that weekend. Unclassified benign example, but you can see the applicability to DoD IC type of applications where you can quickly aggregate this information. And of course, in that example, that was a single algorithm, but we're going to be adding a bunch of different types. So let's identify every object that's of interest and catalog all of those over time, so that we can start putting together patterns of life and start getting that activity-based intelligence going there. Where that's ultimately going to bring us up, and I kind of bring these out in closings, I tie this back to that General Teptula statement that was made at the beginning. In the not too distant future, made all the statements about how the DoD is seeing a just a flood of data, not only in EO, but all the different types of data. That flood is here. We're going to go from drowning in that data with the power of deep learning technology and all of these algorithms we're going to start mass producing into drowning in detections. And how we make sense of that data. We're kind of just pushing the problem from raw pixels over into detections at timestamps. How do we handle all of those in an aggregated fashion? We go from drowning in data to drowning in detections, features, observations. And I think beyond automating all of these, we're going to start to see a shift in the deep learning, machine learning, artificial intelligence from purely staring at pixels to now staring at these detections over time and making sense at a kind of higher order level there, bringing us to our end goal of automated activity-based intelligence. Conclusion takeaway, as I mentioned several times there, deep learning's remove the bottlenecks that traditional computer vision techniques have had, where we needed an image scientist and a specialist on the target we're trying to identify. We can get that very quickly if we've got the label data availability, if we've got the network architecture optimized, if we know how to efficiently train and refine the model, and we know how to get these results out in a way that analysts can use and not be overwhelmed by the data that's being spit out. Through all of the efforts that we're pushing on there in our various different tools across the 5 different layers, we are eliminating those bottlenecks so that we can start cranking these out kind of in mass production format. And that's really the main takeaway here is we're going to see a mass production of deep learning-based GEOINT algorithms. It's within reach. It's here. It's time for a cultural shift of AI adoption. And with that, I'll hand it back over to Jody. I think we'll open it up to Q&A.
Yeah, great. Thanks, Will and Pedro, for the informative presentation. So we have a few minutes for Q&A. So if you have any questions, just enter them into the questions chat box, and we'll get to them. First question, why do you use an LSTM for the clandestine airfields? LSTMs are used mainly for sequential data, and it's pretty impressive that you got a 94+% accuracy.
Yeah, great. Yeah, so that was an example to see the benefit of treating the target as a time series versus a single frame. You know, when Planet was coming online and they were moving to, we're going to have a picture of every square inch of the Earth daily. What can we do with this additional information? That was kind of the comparison we were making, is we can get an accuracy of a single frame at a certain level here, but if I treat it as a dynamic target that I know has a changing signature over its lifespan, you know, it's going to be first built, it's going to be used, some vegetation is going to grow back over, it's going to be created, it's going to be rebuilt. Looking at that entire lifespan as the signature we're trying to identify, that is what helped us raise the accuracy. And we saw similar between the 2 different types of RNN approaches there, but the big takeaway was it was more powerful to look at that time series than just a single frame.
Great. The next question, how soon before your API is extended to the desktop and IDL?
Yeah, sure. So that work's underway. The roadmap's still being planned out. That we've got some things that are rolling out through add-on packages. But I would have to leave it as stay tuned for the rollout date on that.
Yeah, I mean, I can add some more to that. So we also have so MB, you know, which is your flagship product. We have an enterprise version of that called GSF, or Geospatial Services Framework, and we divide them in different engines. You know, for MB, IDL. And we're currently in the process of developing a mega engine, or as we call it here, but it's pretty much a machine learning engine that will be available for doing API calls and requests. But it's still under development. We actually have our own internal version, you know, doing testing and evaluation. But you know, we already have done demos. We have web service demos that we do using that engine, but it's still not a fully commercial product yet.
Great. Will NVPY have a tie into your machine learning solutions?
Yep. Yeah, same thing. Yeah, you're going to be able to, like, once it's in GSF, you know, it's all based on JavaScript and API calls. So essentially, you can create tasks, you know, that are going to be calling machine learning tasks, and you can do it either from MB, from a web service, you can do it from ArcGIS Pro. So, the goal is to make it open source and, being able to tie it up to as many tools as possible.
Great. What is the hardest cybersecurity challenge related to implementing the DL?
Yeah, that's a great question. An area of concern, certainly for everybody. I mean, there's been a lot of public research studies posted out there about the ways poison data sets can trick neural nets, and so it's certainly a concern. DoD's Project Maven has brought that up as things that they're making sure they're securing the supply chain all the way back, both on the hardware as well as the data sets that we're using. It all comes back to explainable AI, being able to understand why the neural net made the decision. We may not know every single feature that it queued off of, but understanding the data it was trained on very well, so we know the distribution it saw and the decision it's going to make. All of that goes in to help harden these algorithms such that we can trust the decision they're making. Active area of concern. I don't know which sub-segment I would put as the highest, but certainly being able to explain the decision that's being made is kind of the overarching concern there.
All right. The next question, not sure if I'm saying this right, but have you compared DIRSIG or DIRSIG results to actual target results? CNNs can be very sensitive to subtle features that DIRSIG might not get right.
Yeah, absolutely. We've got quite a bit of work going on that right now. We've seen concerns from both sides and are seeing really positive results. It's comparing right at the same level as training with the raw data. One of the things we're looking at is, we've heard concerns that it wouldn't be real enough. Those that have actually used DIRSIG notes, we're not guessing at the ray tracing there. We actually have the sensor model, and it's a full physics-based implementation. But it may actually be too good. We may actually be wasting processing cycles on things the neural net could have picked up the information from without that. So yeah, valid concern. We are looking at it to make sure we understand exactly what it's queuing off of, kind of going back to the explainable AI there as well. But the results so far have shown it to be extremely portable. We're getting enough generalization to make the jump over into things it hadn't seen before. And some of that comes down to maybe I don't want to use a 152-layer deep neural network when I've been trained on synthetic imagery. Maybe I want a shallower network so I can generalize better, those type of things.
All right, we got one last question. When training prospective analysts and programmers, what advanced mathematics need to be mastered before digging into DL and AI?
Yeah, that's a great question. I would say understanding the overall concept of neural net application is kind of great foundation information there. I'm not sure that the higher order math is necessarily needed. Mm-hmm. I would give a call out to one of our partners who have partnered with NVIDIA on all of this research in deep learning, and they have a fantastic program in their Deep Learning Institute that covers the ins and outs of the basic information you need to start doing work in this area. And that's a great place to start.
Yeah. Also, I want to add. So every deep learning engine, like Caffe, TensorFlow, Torch, all they have their own documentation. We kind of started with Caffe, and there's a lot of documentation to start with. There's a lot of curated data sets you can start training on. You can create VMs, and start running it on your own. What we have taken is like some of those open source engines and kind of like optimize the architecture for GEOINT, overhead, Lidar, SAR, and multiple data types. But absolutely, you can start on your own. There's also another data set that we used called UC Merced. That one is actually on 21 different classes of overhead imagery. It's a little bit older now, but it can also be used for training your algorithms on the overhead GEOINT space. So definitely recommend using that data set. And as time goes, more data sets are going to be published. So definitely stay tuned. The SpaceNet data set is another good one as well. That one was in partnership with NVIDIA and DG. So definitely stay tuned for that as well. Yeah, there's a lot of documentation, so it could be overwhelming. I can understand that, but definitely start looking into the most popular ones, Caffe, Torch, and TensorFlow.
Great. So with that, we're going to wrap things up. As a reminder, we're going to send you an email with the recording of the webinar and the PDF of the presentation, and you're welcome to send it to whoever you want. We'll also have it available on our website at www.harrisgeospatial.com. Thank you, everyone, for your attention on the line, and thank you, Will and Pedro, for the great presentation. Have a great day.
Thanks for everyone's time. Bye-bye.